So you probably found your way to this little gizmo on GeoGebra, and I'm hoping that you played around with this little thing. So I asked you to look at the slopes of these tangent lines. So the tangent lines are in gray, and the function itself is in green. You can see that it's got a local minimum right here. So whatever this x value happens to be, and then it looks like right here it's got a local maximum. And then down here, it's got a local minimum as well. Okay, so if you look at what are the slopes of these tangent lines, so those are given by this m equals f prime of a that's over on the left. So here it's 0.5036 blah, blah, blah. So if you look at these tangent lines, what's happening to them as you get closer and closer to settling into that minimum value, okay, so you can see that the line themselves, they're getting more and more flat. And that's happening at each one of these points, right? So if we look at here, so there I somehow miraculously got it to be exactly flat. And then right over here as well, so look, they're kind of steep and then they start getting more and more flat, right? Until really they should be fully horizontal at these points, okay? So if you think about what is the slope of a horizontal line, it should really be 0, right? Because it's a constant line, okay? So it's got no slope. So then what that's telling us is that our maximums and minimums really happen at points where the derivative, so the slope of the tangent line, is 0. Okay, and that's what this fact here is saying, right? So if you have local max and minimums, they happen at points where the derivative is equal to 0. Right, and this is really only if the derivative exists, right? So we have a local max or min somewhere in the inside of a domain a to b, if the derivative exists and the derivative is equal to 0. Okay? So we can think about this graph, right? So you can see we have a local maximum right here at C. We have a local minimum right here at D. At both of those places, the derivative exists. It's a nice kind of smooth graph, nothing weird going on with it. So at those places, we should expect that the slope of the tangent line, so the tangent line is this pink line, the slope of the tangent line at C and the slope of the tangent line at D, those should both be 0, right? Those slopes should be 0. Okay, so if we're looking for the points C and D, right, because we want to know where do our maximums and minimums happen, because we want to solve some optimization problem, then really we only have to look for, or one of the things we have to look for is where is the derivative equal to 0. Okay, so now you might look at the other part of this graph, which is what I drew in right here. Okay, so this little part. So you can see this is actually a cusp, right? So it goes up and then down. It's pretty sharp. So we talked about the fact that at these types of places, the derivative doesn't exist, right? So I'll say f prime of x does not exist at this cusp, right? It's too sharp of a cusp. It's too sharp of a change for it to really have a derivative there. Okay, so when we're looking, but it's still, you can still see that this is going to be a local maximum, right? So not only do we need to check where the derivative is equal to 0, like these 2 points, but we also have to check where is the derivative undefined, right? Because we might also have maximums, local maximums and local minimums at those places, right? So let me rewrite f prime of C, f prime of D should be 0. Okay, so that leads us to this next definition, which is critical points or critical numbers. I'll call them critical points. So a critical point of a function f is a number C, so this is an x value C in the domain of f with the property that when I plug it into the derivative of f, I get 0. So that's like one of these 2 points. Or when I plug that number into the derivative, actually it doesn't exist, right? So the derivative doesn't exist at that point. So that would be like this value right here, right? So what's happening there. Okay, so when we're looking for local maximum and minimums, we have to look at these 2 places, right? Where is the derivative equal to 0 and where does the derivative not exist? Okay, because those 2 places can give us the locations of local max and mins. Okay, so for example, let's look at this next problem here. So we need to check two places, right? So check where f prime of x equals 0 and where f prime of x does not exist. Okay, that's how we find critical points, right? Because of this definition, critical points are where f prime of c is 0 and where f prime does not exist. Okay, so let's do this part first, right? So f prime of x equals 0. So if we look at that, so we're given the function f, right? We're asked to find the critical points of f of x equals x cubed minus 3 halves x squared minus 6x plus 3. So we're going to find the derivative, right? So first, f prime of x, so we're going to take the derivative. So, okay, so using the power rule here, we're going to pull that 3 forward, subtract 1 from the power, minus that 3 halves is going to hang out there because it's just a constant. So we're going to differentiate the x squared part. We get 2x. We can see some stuff is going to cancel there. And then the minus 6x, derivative of that should just be minus 6. And then the plus 3, that's a constant, so the derivative should be 0, right? So there's really a plus 0 here, so maybe I'll write it. Okay, so let's simplify a little bit. So we have f prime of x equals 3x squared. These 2's are going to cancel, right? This 2, this 2. So then I end up with minus 3x, and then I have the minus 6. Okay, and I won't write the 0. Okay, so I want to set this equal to 0. So setting this to 0 gives, so we're going to get 3x squared minus 3x minus 6 equals 0. Let's divide everything by 3, okay, just to make things a little bit simpler. So we're going to get x squared minus x minus 2 equals 0. Right, so I just divided by 3, okay, just to simplify a bit. And now we can try to factor, so let's do that. Okay, so we will write an x here. So play around with this a little bit, right? 2, 1, let's make this negative, make this positive. So check again and make sure that it gives you what it should be giving you. Okay, so here we just factored. Factor. Okay. Now we're going to set each of these two terms equal to 0. So x plus 1 equals 0. That gives me x equals minus 1. And this other one gives me x minus 2 equals 0. So x equals 2. Okay, so this gives me two solutions, right? So x equals minus 1 and x equals 2. Right? So those are two of my critical points. Okay. So now, let me add a page on here. Okay. So now we also need to check when f prime is undefined, right? When does it not exist? Okay. But f of x is a polynomial, right? Okay, so if we look at it, right, it's right here. So here's f of x. Okay, it's a polynomial. Polynomials, the derivatives of polynomials exist all the time, right? They always exist. Okay, so we actually don't get any points from the part where this is undefined, right? So the part where the derivative is undefined really isn't going to give us any points. Okay, so maybe we'll write that in. So f of x is a polynomial. And so f prime of x always exists. Okay, so this means we don't get any critical points from the derivative being undefined. Okay, so it was totally enough to just check where the derivative was equal to 0. Okay, but there will be examples where the derivative being undefined gives us some critical points. Okay, so you'll see some of those on your online homework, and I hope you'll ask me questions about those at some point during our class session. Okay, so at the end of the day, let's just summarize. So critical points are so we had one x at, so it looks like x equals -1, and we had another one at x equals 2. X equals -1 and x equals 2. Okay, and this is our final answer. Okay. So now, if we look at this, right, so if we look at where we found our critical points, we found one right here at -1 and one right here at 2. And this is the graph of that polynomial, right, that polynomial. Okay, so if you look at this graph, you can see we do have a local maximum here at one of our first critical points at x equals -1. And we have a local minimum right here at the other critical point we found at x equals 2. Okay, so this is how we're going to find our local maximums and minimums, right? First, we're going to find critical points, and then later on in the next section, we're going to think about how do we determine whether this is a local min or a local max. Okay, so you now try out this example, find the critical points of this next polynomial.